So we'll continue to discuss the covariance and the variance. So for this proposition, we assume x and y are two random variables with finite second moment. Okay, then the covariance of x and y when squared is less than or equal to the variance of x times the variance of y. And equality holds if and only if either y is a linear function of x or x is a linear function of y with probability 1. For some constants, alpha, beta, gamma, and delta. So this is actually a direct application of Schwa's inequality. So we let z equal to x minus to the expectation of x, and w to be y minus the expectation of y. And because x and y has finite second moment, so they have finite first moment, as we have shown before. Okay, so that this definition of z and the w, all right, are well defined. So now by Schwa's inequality, so we have that the covariance matrix of xy square, which is the expectation of x minus expectation of x, and y minus expectation y. Okay, so that is the definition of covariance, and we take the square. So that is the expectation of z times w square. Okay, and the Schwa's inequality says that this is less than equal to the square expectation, the second moment, times the of z, the second moment of w. Okay, and we know this is x minus expectation of x square times expectation of y minus expectation of y square. Okay, and this is exactly the variance of x, and this is the variance of y. Okay. Okay, so we establish inequality there. And now equality holds by Schwa's inequality. If and only if that either Z is equal to alpha W, or W is equal to beta of Z for some alpha whisper V1. I forgot to say whisper V1 for some constant alpha beta. Okay, so that is the if and only condition. And so we plug in back to, so this is x minus expectation of x equal to alpha, y minus expectation of y, okay, or y minus expectation of y equal to beta, x minus expectation of x, okay, for some constant alpha beta. Okay. So that is either. So we move for constant, the expectation of x to the right hand side. So either x is equal to alpha y plus expectation of x minus alpha expectation of y. Okay, so that is the constant. Or y is equal to beta x plus expectation of y minus beta expectation of x. Okay. For some constant alpha beta. And so this is either x is equal to plus delta, or y is equal to beta plus gamma, or some okay. So basically, this proposition is a direct application of Schwa's inequality. Oh, I forgot to put with probability 1. With probability 1. Okay. All right, now the correlation. So with this proposition, we can make a definition. The correlation coefficient of two random variables, x and y, having finite second moment and the non-constant with probability 1 is defined as rho of xy maybe I will state denoted as rho xy is defined as here the covariance of xy divided by the square root of the variance of x and the variance of y. All right. The requirements that x and y have a finite second moment is that we because we want to compute the variance of x and y. Okay. And the requirement that x and y are non-constant with probability 1. Because if x is constant with probability 1, then the variance of x is 0. Okay? And if y is constant with probability 1, then variance of y is 0. And you can't put 0 into denominator. Okay? You can't. So that's why we have to exclude such non-trivial situation. So x and y are non-constant with probability 1. Okay. Okay. So this is the definition. The covariance, right, of xy divided by the square root of the product of their variance. But from this proposition, we know that if we take the square root, this is saying that the absolute value of the covariance is less than or equal to the square root of their product, of the product of variance of x and y. Okay, so that this is equivalent. And this is saying that the covariance of xy is upper bounded by the variance of x and variance of y minus variance of x, variance of y. Okay. Okay. So we have the okay, and so by proposition 7.4.f, okay, by this proposition, we know that the correlation coefficient okay, now because x and y are non-constant with probability 1, so this product is non-zero, right? So they are positive. So you can divide this inequality by the square root of the product of these two variants. Okay, so that so you can see that this is 1 and then minus 1. When you divide, right? Divide this quantity, all right? in this inequality. So you have this one. So you know the correlation coefficients is in between -1 and the +1. Okay? But here, in general case, we can't divide this one because x may be constant with probability 1. Okay. But with this condition, then we can do so. So for position 7.4.g says that xy, again, two random variables with finite second moment and non-constant with probability 1. Okay? So suppose that is the case. Then first one. Then the correlation coefficient rho is equal to 1 if and only if y is equal to alpha times x plus delta with probability 1 for some constant alpha greater than 0, but the delta can be any real number. Okay? Second, the correlation coefficient of x and y is equal to -1 if and only if y is equal to alpha x plus delta with probability 1 for some constant alpha less than 1, but delta in all. Okay? And the proof as an exercise. Okay? So you can go back to look at this inequality. Okay? So basically you can go back to here. Okay? So of course you have equality. So in here, you know, they must have some linear relationship. But the coefficient is positive or negative. Depends on either the correlation coefficient is positive 1 or negative 1. All right. You can judge that. You can check. Okay, you can check that. And this is if and only condition. Okay? So you have to check by yourself. So it's a homework. A remark is here. The correlation coefficient rho xy, right? It's a measure of the degree of linearity between two between two non-constant random variables. Of course, you can say with probability 1, random variables x and y. Okay. Because if we want to know the relationship between two functions, because x and y are functions of a function of sample space, right? So they are functions of outcomes. They are functions of outcomes, and the linear function is the simplest possible relationship between two functions. Okay, so that is. So in practice, people usually want to see the degree of linearity between two random variables. And correlation coefficient is a very good measure, because in this proposition, you know, if the correlation coefficient is exactly equal to 1 or plus or minus 1, you can see that they are really linear with probability 1. Okay, it's probability 1. Okay, so that a value of rho xy near plus 1 or minus 1 indicate a high degree of linearity between x and y. Well, is a value near 0 indicate that that such linearity is absent. Okay. Right. A second observation is that a positive value of rho xy. So if you see that the correlation coefficient is positive, then it indicates that y tend to increase when x does. But whereas negative value of rho xy indicate that y tends to decrease when x increases. Okay. For example, in medicine, suppose X is the dose of certain drug, the dose of certain drug, and the Y is the recovery degree. So if the dose of a drug and the recovery degree has a positive correlation coefficient, then usually the community will claim the drug is effective. Okay, it's effective. If it crosses to 0, that means the drug is useless. Okay, but if negative, that is terrible, right? It's terrible. It's not a drug. It becomes to a poison. Okay, so it's a serious problem, So correlation coefficient is a very important measure in many industries, especially in medicine. Okay, so you have to know that even though here we are talking about some mathematical measure, but that is in the industry, in our real life, they play an important role. Okay. Of course, last one is that if the correlation coefficient is 0, then we know x and y are called uncorrelated. Okay. And it's usually a tragedy if some drug company, they developed a drug for some disease and find out that the correlation coefficient is near to 0. That is really a tragedy, because that means that there is no effect, and all the investment is just a waste. Okay, so that they will lose a lot of money. Okay, so they are called uncorrelated. All right, when the correlation coefficient is they are uncorrelated. Okay. Okay. So any questions? Right, so we will move to the next topic of this chapter, conditional expectation. All right, we discussed conditional probability in chapter 6, right? So we define, right, the concept of conditional probability of an event given that a random variable is equal to a certain value. Okay, so I said this is a definition because usually the given random variable y is a continuous random variable. So when you say given a continuous random variable y equal to a certain real number, this event occurs with probability 0. So you can't interpret conditional probability given a random variable to be equal to some specific value as the conventional conditional probability. No, you can't. So we have to define a new concept. But we have seen that this definition is quite useful. Okay, because we developed a theory how to use that to solve the practical problems. And similar situations here. Okay, because when we discuss the reason why we define conditional probability of an event given that a certain random variable equal to some specific value, it is because that we want to compute the probability of that event. But usually, the probability of that event is hard to compute directly. But it becomes easier if we know the conditional probability. Okay, and practical situation give us the answer of conditional probability naturally. Okay, so we can develop the theory, and then we can compute the probability of a certain event. Then the situation will turns out again that usually we want to compute the expectation of certain random variable. We say x, so we want to compute the expectation of x, random variable x. But it seems difficult in many situations. And it quite natural in many situations that we know we can define something called conditional expectation of x given another random value y at a certain value. Okay? And so that is called a conditional expectation. So once we know the conditional expectation, we can compute the expectation of x again. Okay? So the idea will be quite similar to the way we discuss conditional probability. Okay, but in here we will give more properties. Okay. Suppose x and y. So we started with two random variables, two discrete random variables. All right. So we started with simple case. So x, y, two discrete random variables. And recall. So first of all, we recall that the conditional PMF of x, all right, given that y equal to d to y is defined as little p x y into x little y. Okay, it's defined the following way. It's the conventional conditional probability. Okay. And so this is probability of x okay, so that is the joint PMF divided by the marginal PMF. So if the denominator, if this is positive, and we define this to be just P, this is okay. If is equal to 0, okay. So we define the conditional PMF, and this is good for all x in R. Okay, so that is the conditional PMF we defined before. Now, the conditional expectation, okay, the conditional expectation of x given that y equal to d2 y is defined as, okay, so the notation is here. X P defined to be P. Okay. All right. So you from here you can see by our construction. This is our construction. This is by definition. You know, this is our construction. That for every given y, the conditional PMF is really a PMF, a probability measure. Okay. So it's really a PMF. Okay. And so we can define the expectation in this formula. Okay, remember the sum is actually countable sum. Okay, because that only countable many possible value for x. Okay, and so that is there are two ways to go. The first one is x and p x and divided by, okay, and the other is x and the p and the PMF of x. Okay, if so this is expectation of x. If so if for some y such that the PMF of y is 0, then the conditional expectation of x given capital Y equal to this little y is equal to the unconditional expectation of x, by definition. Okay, this is our definition. Don't forget that is definition. All right, but if the PMF of random variable y is positive at little y, then the conditional expectation of random variable x given random variable y equal to little y is this formula. Okay, is this formula here. Then this one usually different from the expectation of x, right? Any questions? Now, if x and y are independent, all right? So suppose x and y are independent, then we know the conditional PMF of x given that capital Y equal to little y is equal to the marginal PMF of x. Okay? So that for all x and for all y, okay, no matter what this value is positive or 0. Okay? So when x, y are independent. So in this case, and the expectation of x and y becomes to, because this is by definition, okay, by definition, and we use this equality. So we have that for all. Okay. So when x and y are independent, then the conditional expectation of x given capital Y equal to y, okay, this quantity we define here is exactly equal to the unconditional expectation of x for all little y in R. Okay? Okay? So now but anyway, in any case, well, either x and y are independent or not, but just we define here, okay, the conditional expectation, okay, the conditional expectation of x given that capital Y is equal to little y. It's a real valued function. So it's a real valued function on Y in R. And can be denoted as G of Y. Okay? So actually, you can see, although we have the name, say, expectation, right? Or conditional expectation, but reality, mathematically, it's a function, a real value with a function of Y in R. For every, so we can denote it as GY. So you can use that the G function that, okay? Okay, so it's a function. So that means that we don't, we are not specify that. Let me know any question if you have up to now. Because we are now in a crucial step here. So you have to realize that conditional expectation of random variable x given that random variable y equal to little y is a real value function defined on the set of all real numbers. Is that okay? All right. Now, the function g of y will be denoted as this notation. Okay, so that's for an outcome omega in the sample space we have okay, so now this is a random variable. So this notation is a random variable. And this random variable actually is a function of y. Okay? It's a function of y. So this is actually the gy, right? Because this is a rename of g of y, right? And g of y is a composition of two functions, g function, y function. So this is g of, okay? And what is g? G is here, right? So g, so this is okay. And we will call this one. So this one we'll call the conditional expectation of x given y. Given y only, right? Not given that y equal to little y, no. Just given y. So this is a notation. And this notation is called by this name. The conditional expectation of x given random variable y. Okay, so what is this? The nature of this one? It is a random variable, and it's a function of random variable y. And what is the associative function g? Well, g is the function, right, which we defined before. Okay, it is the conditional expectation of random variable x given that random variable y equal to some specific real value little y. Any questions? Okay, so we take a break here for 5 minutes. Okay, so let's continue our discussion. So I have been asked a question, but I think that is a good illustration about Z, G. You know, G of Y, right? We define G of Y to be this notation. Actually, G can apply to, for example, Z, right? This is it's a random variable. Then G of Z is also a random variable, right? G of Z is also a random variable. So G can compose arbitrary random variable, not necessarily Y. Okay, not necessarily Y, because G is a function. Okay, and so if you apply to Z, then its value at an outcome omega. It's so that this is actually okay, this value. So the little y is determined by the random value of Z. Okay. And then it will involve three random variables, x, y, z. Okay, and then you will ask yourself, is that a good one to solve your question? Okay, so that is another dimensions you have to ask yourself. Okay, but in here, if we apply Z again to Y, okay, then we have some specific meaning, and we will state that later. Okay, so G of Y is very special because when we construct G, we are using X and Y, right? So Y is involved. And then we use G to do the composition with Y again. Then this random variable should play some important role, right? Should play some important role. And we name this one. So we give G of Y a special name here. A special name here. Okay? So conditional expectation. So this random variable tells us that because of that, when we observe Y, then through this function G, we know something about the expectation of X. Why? Because once we know Y, okay, and by the composition, okay, we know this. So for this specific measurement result, you know, Y of omega is that Y is the measurement device. Omega is the outcome of our random experiment. And Y omega is the measurement result. With this measurement result of Y, we know the expectation of X. So we know some information about X. Okay? And different measurement results give you different information. So it's random. Okay? So that this one is a random variable and it's a function Y because it depends on your measurement result of Y. Okay? So that it's very reasonable to call it as the conditional expectation of X given Y. Given Y. You have to observe Y first. Okay? All right, so now So now we prove a major result. 7.5.1 discrete case. Okay, so the textbook give us proposition 7.5.1 with the two cases, discrete case, absolute continuous cases. But I will give you 4 different cases, right, related to the 4 different definitions of conditional probabilities in chapter 6. Okay, so this is the first part, the discrete part. So now x, y be 2 discrete random variables. Okay, 2 random variables. If x has a finite expectation, then then this function is finite for all. Okay, so it's well-defined function. Okay, because in our definition we haven't yet verified, right, this fact that it's really a function or not. But if x has a finite expectation, then our definition there, this one is finite for all y in R. And the expectation of x can be computed by the expectation of g of y. And by our notation, so this is okay. All right, and what is that? So this is y, and g of y, probability of y. And this is right. So you first look at this one. The original expectation of x can be computed by the expectation of g of y. Okay? And the g of y, so it's a function of y, right? So from the expectation of function of a random variable, you know, this is this formula. Okay? And this is equal to this one. Okay. And that is by the notation. So it gives you a notational advantage. It says that to find the expectation of x, you first of all find the conditional expectation of x given y. And then you find the expectation again. So you can do it in 2 steps. So this one gives you conceptual advantages. But the computational advantage is here. You have to follow G function. Okay? You have to follow G function. Okay. But when you become familiar with this computation, then you will gradually accept this notation, because this is conceptually simple. Okay. So any question about this? Any questions? Right? If no, then I will give you a proof. All right, so since x has a finite expectation, the positive part is finite, and the negative part is finite again. Because we have to show that this is always finite, okay? So maybe it's a little bit sometimes confusion, but so okay. Whenever I write this one means that this value is this exists and is finite. Okay. So it is a very basic factor, so that we have to resort back to our basic idea. All right, so now since the positive part, what positive part is okay, is about the possible value which is greater than or equal to 0. Okay, so that is the expectation by its definition. Okay, you see here. Always remember the sum always is countable, because x and y are discrete. Okay, x, y are discrete. All right, and so we can exchange the summation, the order of summation. Okay, because everything is non-negative. X is non-negative, this is non-negative, so we can exchange the order of, okay. Okay? Because are non-negative. Whenever you have a non-negative integrand or summand, double integral can exchange the order, double sum can exchange the order, whatever. Okay. Okay, and now we can sum over all y such that the probability is greater than 0. Because if this probability is 0, then the joint probability is 0, of course. Okay, so we can just concentrate on this one, x. Things implies okay. All right, and so now we can put this probability here, but divide the same probability there. Okay. And remember, what is this? This is the P y, right? Okay, so now, and we know this is finite. Okay, here this is finite. So this is finite. Okay, and the probability always positive. So that this is sum. This is sum always non-negative, right? Because x is non-negative. And this conditional PMF is also non-negative. Okay, so this sum must be finite. Why? Because if this sum for some particular y, this sum is infinite, then an infinite number times a positive number is infinite number. Okay. Okay. So that summation 0 x p is finite for all y such that greater than 0. Use with. Okay. Is that okay? All right. Similarly, we can do so. Since expectation of x minus is finite, so you can do the same thing. The sum, summation x less than 0 minus x and the P is finite for all y with Py y greater than 0. Okay, I omit the detail, but you can follow the same thing. Okay, so that is they are finite. Okay, then now the expectation of x so now for all y with P of the PMF of y greater than 0, the conditional expectation, given that capital Y is equal to this little y, becomes to summation of x of P. Okay, and then you can raise up to plus, so this is become 2 minus okay, become to sum of these two partial sum. And you can see they are both finite. So this is finite. And this things for all also for all y with equal to 0, the conditional expectation is equal to unconditional one by definition. So this is finite. Okay. So we conclude that expectation of exists and is finite for all y in R. Okay, so G of y is well defined. A function is well defined functions. Okay. And we have this result because x has a finite expectation. Okay, x has a finite expectation. Okay, then the rest will be easy. The rest will be easy. So now, the expectation of the conditional expectation given y, this is random variable. So the expectation of this random variable we know is the expectation of G of y. Oh, I forgot to put. So we conclude that Okay. All right. So and so that okay. So we compute this expectation. Okay, and this is actually Py. Okay, and so we will sum over y such as the marginal PMF is positive, because when Py, the marginal PMF of at y little y is 0, then no contribution at all, right? So that's so this is summation x and this is okay, this one. Then you can cancel. So this is become 2y. Summation x and p, x, y. Okay. Okay. Now we have to go back. So the sum, the first sum is over all y such as the marginal PMF of random variable y at little y is positive. But we can sum over all y. Things implies that P okay for all x. So if we include all y such as Py of y is 0, then we'll have no problem because that the corresponding joint PMF is 0. Okay, so that we have equality here. Okay. And the sum Okay, so now things. Now we can exchange the order of x, y. The reason is I can see since the expectation of x, which is okay, and I think this one, the absolute value of x, because x has finite expectation, so both of the positive part and negative part have finite expectation, so that their absolute value, its absolute value has finite expectation. But when we look at the expectation of the absolute value of x, you see here. So this involves the sum here. And when we see it, the involve that okay. So this is the same as so that this double sum, these two double, because the summand are all non-negative, so that you can exchange their order of summation. So that it converged absolutely, because you see this, you have absolute value, so that the same. Once this is true, because they are all finite, so that the corresponding summation can exchange the order of expectation. Okay. So absolute convergence implies convergence of these two sums, and they are equal. Okay. Right, and so now we have so this is P of x, and this is expectation of x, and we have down. Okay, so the equality is because we can exchange the order of summation is because the absolute value of the summand converge. Okay, they are all finite value. Okay. Okay. So I think the harder part of this proof is to show that the gy is actually is indeed a function from R to R. Okay. So that the function exists and is finite when x has a finite expectation. So this is so we spend some time to do so. And then we verify that the expectation of this random variable is indeed the expectation of x. Okay, so I can make a remark here. The above proposition tells us that we can compute the expectation of a random variable by conditioning. Okay. So now I will show you how to use this proposition by an example here. It's an example in the textbook. It's about the expectation of a sum of a random number of random variables. Okay. All right, so that's n. A random variable modeling the number of people entering a department store on a given day. Okay. And the x sub I is the amount of money spent by one of this customer. By anyone of these customers okay. So which is it's a random variable with the same same mean, say of $8, and independent of each other. Okay, so the amount, the same mean of $8 and independent of, and independent of, and the number of people entering the department store. Okay. All right. So the question is, what is the expected amount of money spent in the store on a given day? Okay, on a given day. So, all right. So, so we let Y be the total amount of money spent by this M people. Okay. So now Y, so for each outcome omega in the sample space, Y omega would be equal to, so we have n of omega customers entering the department store, and each customer, the ith customer, will spend xi of omega amount money. Okay, so that is the situation. Okay. So our purpose is to find the expectation of Y. Okay. So to find the expectation Y, we will find the expectation of Y given the number of customers, capital N, into the department store. So we want to use this identity. All right, so we have to find the conditional expectation Y given capital N. Okay, but before to do so, here okay, so now we compute the G of N, right? So G of N okay, so this is actually, and the G of N, so it's expectation I from 1 to N xi. But given that the number of customers entering to the department store is little n, So the sum is little n and the xi. Okay? Now, because xi's are independent of the total number, the number of customers entering the department store, and we know if so, the sum is also independent of n. Okay, because xi's are independent of n, so their sum is also independent of n. So that this is equal to this one. Okay, because we have noted this one, right? So since xi's are independent of capital N, okay, and so that by linearity, okay, and this is A times n dollars, because each x sub I is the mean of each SI is $8. Okay, so it's 8 times n dollars here. And so you can see this is a function of little n, right? 8 times n, a little function of n. Okay, so we plug into here. Okay, so this is expectation of 8n. So it's 8 expectation of n. So that g of n is equal to 8n. Okay, and we look to here. So this is 8n, and I forgot to say that the n. So we have to say it's a random variable, right? With mean in here, 50. So the mean of the number of customers entering to the store is 50. So 8 times 50 is 400. Okay. So $400. Any questions? Because we already know that the number, because given that capital N equal to little n, so we know the number of customers entering to the store is little n. So that we condition on this one, right? So we know that. So capital N can be replaced by little n. And then, so we have a finite number of xi summed together, right? But because each xi is independent of n, so their sum is also independent of n. By proposition 6.3.d. Oh, no, E. Okay. Okay, the E there. And then I think so. This implies that their sum independent by proposition 6.3.e. Okay. Yes, please. Oh, in here, right? In this, okay. You can think about that because this is we have a randomness in this because in different days there will be different number of customers enter into a department store. Okay, so you can think about an omega could be a day. Okay, to be a day, and in different day you have a different number of customers into that. And for a customer get into a department store, you may think about in different days, customer will spend because they are moved. Maybe that day will be a birthday of that person, or maybe a birthday of his or her parents or siblings. But maybe that day, she or he, maybe he, right, broke with his girlfriend. So he is heartbroken, so he don't want to spend any money, just walk into that. Okay, so it depends on, right? It's different days, different persons will have different mood, and so they will spend a different amount of money, so that because they are different persons, so different person may spend different. The amount of money spent may be independent of each other, right? It's a reasonable assumption of there. Yeah. So yeah, omega you can think about that different days, different persons. Okay, of that, all the factors together, and it's really random. Right? There are many factors, not only the day. Okay, maybe it depends on years. For example, this year is not good. Inflations, the Russian-Ukraine war, a lot of different incidents of the world. Okay, compared with 10 years ago or 20 years ago. So all the environment changes. So omega, maybe there are many factors, and it's hard. So that's why sometimes for a simple problem, I will ask you to write out the probabilistic model, right? But for some problem, that would be very difficult. So I dare not ask you to write down the probabilistic models. And instead, I will give you the model already. Okay, so if a problem give you a random value with some distribution, also that means that the probabilistic model in behind is very complicated. Okay, and that is the usual case, especially if you are an economist, all right, and or your banker, that you have to consider a lot of factors. Even though you are an engineer in a manufacturing company and handle about quality control, it is still a very big problem with that. There are so many factors to consider to build your probabilistic model. But if you are able to build your probabilistic model, that would be very exciting and very important if the model is reasonable. Good, okay? And people trying to do so. You know, everybody, a lot of smart people trying to find out a suitable and useful probabilistic model. But many failed, okay? Some may be successful. But once you have, then you can start your deductive machine. You learn in this course. You have a lot of consequence. That is mathematics. It's very precise. Okay, and you will achieve a lot of benefits. You know, that is true, especially in the stock market. Smart people in the world, many smart people in the world, want to find the probabilistic model of the stock market. Okay, if you one of the smart people and try to find a probabilistic model of Taiwan stock market, then you will become a very, very rich person. Okay, that would be, you will earn a lot of money, bigger than lottery, you know, because you will earn a lot of money every day, not once or twice in your life. Okay, you will earn money every day. Okay, but that is very extremely hard. You know, extremely hard. Okay, so you ask a very good question. What is the behind? What is the probabilistic model? That is really always the fundamental question you should ask. Okay, you should ask for that in your life. Okay, in your life. But don't forget your machine here. Sometimes it will help you to find out a good model. Okay, a good model, because you can have a conjecture and deduct some consequence, compare with the experiments, compare with the truth, and to modify your assumptions back. And you will try that in many iterations, many iterations. That may spend years for you. Okay, but that would be valuable, right? Okay, other questions? Okay, great. So anyway, because I will go abroad on May 17. So last week, next week will be the last week I will give in-person lecture. Okay, and then I will, because we have three early makeup lectures already, right? Now I'm doing some pre-recording. So I will ask our TA to broadcast my recording on YouTube. So you will watch my recordings in the last 2 weeks to prepare for the final examination. I already finished the recording of chapter 8 already. Okay, and this week I will do a little part of the last 2 sections of chapter 7. So I think that's why I spend some time to study some examples for you, because I think that is valuable, and so please watch the recording. You can say that would be the asynchronous online learning. Okay, I will adapt this semester. Okay, so I'll see you next week.